Hello everyone, in this video we will be learning about partition functions in a quantum system. So a partition function comes from a way of counting particles of a system when the particles are distributed over the available energy levels. For example, in a statistical mechanic, partition function describes the statistical properties of a system in thermodynamic equilibrium. It is a function of temperature and volume and other parameters. Most of the aggregate thermodynamic variables of the system, such as total energy, entropy, and pressure and free energy, can be expressed in terms of the partition function or its derivatives. Alright, so a practical question arises is how the molecules are distributed over the energy states at a given temperature. In order to answer this, we must refer back to the Boltzmann factor, which is exponential of an energy to the kT, where k is the Boltzmann constant. So the Boltzmann factor is essential because it tells us if a system has energies in systems with different energies. And this tells us the probability given that an energy of a given energy. So once we sum all this all these probabilities, we know that the sum has to equal 1, which means that our normalization constant is 1 over q, which we could write as q. Which we could write the summation of our Boltzmann factor is equal to q, where q is our partition function.
Examples that the partition function could describe is an ideal gas. In this example, there is a piston, and in the first case, we have a compressed gas with high energy particles at a high temperature, high pressure, small volume. In the second phase, where the gas expands as the piston moves up, we have particles that are less excited, they're lower energy. That results in low pressure, low temperature, and high volume. And the ideal gas law that describes a gas properties is PV equals nRT. Now, the way that you could derive this ideal gas law using partition function for a monatomic ideal gas, shown here in Q, is by plugging it into the equation for average pressure. And the way to do this is by taking the natural log of Q. So taking the natural log of this function here, and the way that is done is it is represented as ln of Q. That way we have a difference in natural logs. We have our denominator here as a negative natural log, and we bring this power here down to the coefficient. And so if we take our partial derivative with respect to volume of this natural log of Q, we get n over v. And if we substitute this back into the average pressure, which is this equation up here in this position, we get this expression here. And by doing some rearrangements, we end up with the equation for an ideal gas, the ideal gas law.
Alright, so now that we understand how partition function can relate to ideal gas, we can also relate partition functions to a particle in a one-dimensional box. And as you see here, we have the typical energy for a particle in a box, h squared times n in the x direction, your quantum number, over constant 8 mass times your length of your box in the x dimension, where we have a beta constant, which is going to be 1 over Boltzmann's constant times the temperature. Alpha can involve this beta term to break down the equation more simple, as well as x squared. So this will enable us to produce an integral out of the summations of this partition function, where you can see that through the use of an integral table we would get half times the square root of pi over what alpha had became, which is why it made convenient to use these terms, due to the result of the integral of this partition function for the particle in a box for one-dimensional translation. And we can from here display an example which can relate to argon atoms confined in a box, one-dimensional, of length 2 micrometers. So using the equation we just derived with the help of particle in a box, to remind you what beta is, 1 over Boltzmann constant times temperature, and Boltzmann constant is relevant to ideal gas constant over Avogadro's number. We can see how the dimensions come together in this partition function, where we have the length of the box, Planck's constant, the constants of the integrational term that accumulate the partitions into a system, and you can see here these units will cancel to give us a dimensionless factor, which most partition functions are accommodated when they're integrated into a large system. And here in our example for argon, we get about 1.32 to the negative 6 for our partition function constant.
So other applications of the partition function can include car pistons, steam engines, rockets, boilers, and bombs. Now that we have an idea of what the partition function is, how to use it, and some examples, we'd like to thank you for watching our video on partition functions related to quantum systems.